Welcome back, everyone, to the Deep Dive. Today, we are diving headfirst into something that's just, well, completely reshaping how we create visuals. We're talking about the truly astonishing, fast-moving world of AI image and video generation. And forget simple filters, right? We mean systems creating hyper-real images, even cinematic video, just from text. The speed of innovation, just in the last couple of years, it's been transformative, really. So our mission today is to cut through some of that noise, understand the tech, the clever ideas behind it, and the tools making it happen. We'll look at things like diffusion models, LoRA, all that stuff, putting power in your hands. Think of this as your shortcut, basically, getting you those aha moments without drowning in jargon. Okay, let's unpack this.
It's definitely a dynamic space. And what's fascinating here isn't just how sophisticated it all is, it's the speed. The sheer speed at which this stuff became powerful and accessible. We're really seeing, a democratization of these advanced creative tools. It's quite something.
That accessibility is huge, yeah. So let's start right there. For anyone wondering how these incredible images, these videos actually get made, where do we even begin? We used to hear a lot about GANs and VAEs, right?
Yeah.
But something big shifted.
Oh, absolutely. Diffusion models have pretty clearly taken the lead for top quality image generation now. I mean, generative adversarial networks, GANs, they were groundbreaking, no doubt, but often tricky to train. And they could sometimes get stuck in a rut, that mode collapse thing where they only produce certain kinds of images. VADs, variational autoencoders, were generally more stable, but the results could be a bit blurry. Diffusion models, though, they offer this really robust, high-quality approach. The core idea is actually quite elegant. They learn to reverse a process of systematically adding noise.
Okay, so wait. You start with a clear image, add noise till it's static, and the model learns to undo that step by step, kind of like unscrambling it.
And exactly. That's a great way to put it. It breaks down this really complex task making an image from scratch into lots of small, manageable denoising steps. Imagine just pure random noise, like TV static. And then, step by step, the model refines it, predicts a tiny bit of the noise, removes it, predicts, removes, until eventually a coherent image emerges. And this careful, iterative process, that's key to their stability and the amazing quality and variety you get.
Right. And here's what gets really interesting for practical use, isn't it? Because generating pixel by pixel from noise, that sounds like it needs a supercomputer. How did they make this actually usable for us?
That's the crucial breakthrough Stable Diffusion brought to the table. The key innovation, the big idea, was doing that diffusion process not in the full pixel space, which is huge and computationally heavy, but in a much smaller, compressed, latent space. This approach, originally called latent diffusion models, or LDMs, it just slashed the computational needs while keeping the quality really high.
Latent space.
Yeah.
Okay, sounds a bit abstract. Can you break that down? Why is working there such a game changer? What does it actually unlock?
Well, think of it like this. Instead of directly manipulating, say, millions of pixels for a big image, which is incredibly demanding on your computer's memory and processing power, you're working with a much smaller, more efficient blueprint or the essence of the image. This cuts down memory needs dramatically. It speeds up training and image generation hugely. And it means you can work with higher resolution images without the computational cost just exploding, like a standard 512 by 512 image that's over 250,000 pixels.
Oh, yeah.
But it might be represented as, say, a 64 by 64 latent map, much more manageable, right?
Oh, okay. Yeah, that makes sense.
And this is really why Stable Diffusion exploded onto the scene. It put this power onto consumer graphics cards, not just research labs. The architecture itself is quite neat and modular, too. You've got a VAE, the variational autoencoder, squishing the image down to latent space and back again. Then a UNet network does the actual denoising work in that latent space. And for text-to-image, you need text encoders like CLIP to translate your prompt into something the UNet can understand.
That's brilliant, making these careful things efficient. Okay, so we have these amazing base models. They can generate incredible stuff from text.
Yeah.
But what if you want to teach it something specific, like the exact look of your dog or a unique art style you've got? What's the trick for that kind of deep personalization?
Now you're talking about LoRA. Low-rank adaptation. That's been a real paradigm shift for fine-tuning these big AI models. It tackles the massive compute and storage problems you hit with traditional fine-tuning, where you'd have to tweak all the model's parameters. The core insight, the clever bit, is that when you adapt a huge pre-trained model, the essential changes needed to learn something new are often quite small, mathematically low rank, which means you can represent those updates using much, much smaller pieces of data.
So, it's like instead of rewriting a whole encyclopedia volume to add one new fact, LoRA just adds a really smart, concise footnote that modifies the existing text.
That's a fantastic analogy, exactly. Instead of changing the model's entire huge set of weights, LoRa decomposes the change needed into two much smaller matrices. Think of them as adapter layers. During training, the original massive model stays frozen, untouched. You only train these small, new adapter matrices. And the efficiency gains are huge. Adapting a giant model might go from needing to train billions of parameters down to maybe just millions. This slashes the GPU memory you need, often by around 3 times, sometimes more.
Wow.
And in practice, it means super fast customization. You can train a LoRa for a specific art style, a character, an object, all without retraining the whole base model. It's what really opened the door for individuals and small teams to personalize these powerful tools.
And how much data do you need? Is it a huge process?
Surprisingly little, often. Maybe 10 to 100 images can be enough for a decent LoRa. And training can often be done in hours, not days or weeks. Plus, you can combine LoRa's, mix the style LoRa with the character LoRa, for instance.
That's incredible. So much flexibility. Okay, so that covers customizing the style, the subject. But artists also need control over the where and how, right? The composition, the pose of a character. How do we get that level of control?
Right, that's exactly where ControlNet comes in. It was designed to tackle that lack of precise spatial control in early text-to-image models. ControlNet adds extra trainable layers to the model. These layers let you condition the generation process on different kinds of spatial information. So you can feed it things like an edge map, basically, an outline drawing or depth information, or even a skeleton showing a human pose.
So you give the AI a kind of structural blueprint to follow, making sure things are where you want them.
Precisely. And the architectural trick is really clever. It uses what they call zero convolution layers. These new control layers start out initialized with 0, so initially they do nothing. They don't interfere with the base model. Then as they train, they gradually learn how to inject your spatial guidance, the pose, the outline, without messing up all the knowledge the original model already has.
So it preserves the base model's quality while adding control. Smart.
Very smart. It keeps all that artistic capability intact. And you get specialized ControlNet models for different tasks. Canny edges for fine lines, depth maps for 3D layout, pose estimation for characters, and you can even stack them. Use a pose ControlNet and an edge ControlNet together. Maybe weight one more heavily than the other. Really complex control becomes possible.
Okay, we've got styles of LoRa, composition with ControlNet, but what about that very specific thing? Like, I want pictures of my cat, Fluffy, doing different things, or my company's unique logo on different products. How do you nail one specific subject?
For that level of subject specificity, you'd likely turn to DreamBooth. DreamBooth is all about injecting a specific subject into a diffusion model using targeted fine-tuning. The core mechanism involves associating a unique, often rare identifier token like a special word with your subject during training. And crucially, it uses something called prior preservation. While it's learning about, say, your specific dog, it also generates other images of generic dogs or other objects to stop the model from completely forgetting everything else it knows just to learn about your pet. It preserves its general knowledge.
Right, so it doesn't overfit just to that one subject. How does the training actually work for something like DreamBooth?
It's surprisingly efficient now. You generally need just a handful of good images, maybe 3 to 5, showing your subject from different angles, different lighting. Then you pick your unique trigger word, something the model doesn't already know, like the fluffy cat.
Yep.
You train the model on your images paired with prompts using that trigger word. And modern tools, interfaces like Koha's GUI, for example, have made this super accessible. Training can often finish in like 10-15 minutes on decent hardware.
10 to 15 minutes. That's amazing. Makes creating genuinely personalized models really feasible for almost anyone.
Okay, the level of control over static images is just mind-blowing now. But let's shift gears. We've covered generating and customizing stills. Now bringing them to life. Video. How does this diffusion magic extend from a single frame to motion? Yeah, video generation is the next big frontier, and it builds on the same core diffusion ideas. Essentially, these models learn to treat video not just as a sequence of images, but as collections of spatiotemporal patches. They understand space and time together. And right now, the model making the biggest waves, the clear state-of-the-art, is OpenAI's Sora. Sora uses a transformer architecture, similar to large language models in some ways, but operating on these space-time patches. These patches can come from videos or even still images, which is interesting. And a really key architectural choice they made was training it on data in its native format, different durations, resolutions, aspect ratios. They didn't force everything into a standard square box like older models often did.
So it learns from a much wider, more realistic variety of video data. That sounds like it would make a big difference.
Exactly. It allows Sora to generate video across a huge range of formats, up to 60 seconds long currently, which is quite impressive. And its capabilities go beyond just text to video. It can animate still images, making them move. It can extend existing videos, predicting what might happen next or what came before. It can even do video-to-video editing, changing styles or elements while trying to keep things consistent over time.
And you mentioned something about understanding the physical world. That sounds ambitious.
It is, and it's maybe the most fascinating aspect. Sora shows glimpses of understanding things like 3D consistency objects looking right as the camera moves, object permanence knowing something still exists even when it goes behind something else. Even basic physics interactions seem to be simulated sometimes. It's not perfect, of course, but it suggests these models are learning more than just pixel patterns. They're learning underlying world models. Oh, and they also have Sora Turbo now, focused on improving the generation speed, which is always crucial for actual use.
Sora sounds incredible, almost like a nascent world simulator. But it's also maybe not something everyone can access easily right now. What about other video generation tools that are perhaps more widely available or cater to different needs?
Good point. While Sora grabs headlines, there are other really strong players. Runway ML, for instance, their Gen 3 alpha model is very powerful. Runway tends to focus more on creative professionals. Gen 3 is excellent at generating expressive human characters, handling complex camera movements, and it offers fine-grained control over timing, partly because it was trained on very detailed descriptions of actions over time. It does both text-to-video and image-to-video.
Okay, so Runway for more pro-level control. What else?
Then you have Pika Labs, or just Pika. They've built a really strong community and take a more experimental, sometimes playful approach. Pika has unique features like their ingredient system for visually combining elements in a scene. And they have these creative tools like Peel It, Poke It, Tear It that let you apply dynamic effects to parts of the video. It's very popular for social media content, unique visuals.
Interesting. Different tools for different vibes. Okay, let's circle back for a minute to the core image models. Because Stable Diffusion isn't the only game in town. And even it has evolved significantly, right?
Definitely. The landscape keeps shifting. Look at OpenAI's DALL-E series. DALL-E 1 was an autoregressive transformer, quite different. DALL-E 2 pivoted to diffusion, which was a big step up in quality and coherence. And DALL-E 3, the latest, really focused on nailing prompt following. Understanding complex instructions accurately, plus its integration with ChatGPT helps users craft much better, more detailed prompts. That shows the trend diffusion plus better language understanding.
Right. And the Stable Diffusion family itself, what are the key milestones there?
Well, you had the original SD 1.x models like 1.4 and 1.5. They laid the groundwork, proved the latent diffusion concept worked incredibly well. Around 860 million parameters, usually best at 512 by 512 pixels. Then came Stable Diffusion XL or SDXL. That was a major upgrade. Much bigger internal network. The UNet is about 3 times larger. It uses 2 different text encoders, CLEP VITG and OpenCLP VITL, working together to better understand prompts. And it was designed for native 1024 by 1024 generation, double the resolution.
What specific improvements did SDXL bring beyond just size?
Several key things. Better handling of different aspect ratios thanks to size and crop conditioning during training. A 2-stage process usually.
Yeah.
A base model generates the image, then an optional refiner model adds fine details. This led to just generally better image quality, much improved ability to render text legibly within images, and noticeably better human anatomy, fewer weird hands, for example.
Fewer weird hands is always good. And what about speed? SDXL sounds bigger, so slower.
It can be, but then they released SDXL Turbo. This uses a technique called adversarial diffusion distillation, or ADD. It basically distills the knowledge of a slower, high-quality model into a much faster one. SDXL Turbo can generate really good quality images in just 1 to 4 steps. We're talking like 200 milliseconds for a 512 by 512 image on decent hardware. It's incredibly fast.
Wow, 1 to 4 steps is amazing. Okay, what's the absolute latest buzz in open source image models then?
Right now, a lot of excitement is around FLUX.1. This comes from Black Forest Labs, a company founded by some key researchers who originally worked on Stable Diffusion. FLUX.1 is different architecturally. It uses a rectified flow transformer approach, not a UNet. It's quite large, around 12 billion parameters for the main version. They released it in a few flavors: Schnell for speed, Dev for development, and Pro for top quality. Early results show it's really strong, particularly at generating clear text within images, handling complex scenes with multiple subjects, and maintaining style consistency. It looks very promising.
Okay, so we have all these incredibly powerful models, SDXL, FLUX up.1, DLE3, and the customization tools like LoRA and ControlNet. But what does this mean for someone who just wants to use them? What are the actual interfaces? How do you interact with this stuff day to day?
That's crucial, right? The interface really shapes the experience. And there are a few dominant options catering to different users. For a long time, the go-to standard for many power users has been Automatic 1111, often just called A1111. It's a really comprehensive web UI built with a Python library called Gradio. It gives you access to basically everything. Tons of samplers, settings, integrates LoRa, ControlNet, custom VAEs, detailed prompt weighting. It's packed.
So A1111 is like the Swiss Army knife. Mature, lots of options, big community.
Exactly. Its strengths are its maturity, tons of documentation and tutorials online, and a huge community developing extensions for it. It excels at the traditional workflows. Text to image to image, in painting, out painting. Very robust.
But I've also heard a lot about Comfy UI lately. That seems different. What's the deal there?
Comfy UI represents a totally different philosophy. It's a node-based interface. Instead of menus and sliders, you build your image generation process visually by connecting nodes together on a graph. One node loads the model, another encodes the prompt, another connects to ControlNet, another does the sampling, another saves the image.
Ah, like visual programming for image generation. Sounds potentially more complex, but maybe more flexible.
Precisely. It offers complete workflow customization. You see exactly how data flows through the process, which helps you understand it better. It's often more memory efficient because it only loads what's needed for the current workflow. And it's fantastic for building really complex multi-stage pipelines or using advanced features like running parts of the workflow conditionally or in loops. It's very powerful for advanced users.
Okay, so A1111 for comprehensive features and community, Comfy UI for ultimate flexibility and process visibility. What about developers?
For developers or researchers who want to build their own applications or experiment programmatically, the key tool is the Hugging Face Diffusers library. Hugging Face is a major hub for AI models and tools, and Diffusers provides a standardized Python API for working with diffusion models. It handles things like automatically downloading models, provides optimized code for different hardware, offers various sampling methods, schedulers, and lets you easily swap out components. It integrates really well with the rest of the Hugging Face ecosystem, making it ideal if you're building something custom in Python.
Right, so different tools for different folks, from casual users to deep researchers. That makes sense. Now, these advancements are just, well, mind-blowing. But let's be real. It's not all perfect digital magic yet, is it? What are some of the limitations, the challenges these systems are still grappling with?
Oh, absolutely not perfect. There are definitely still hurdles. You mentioned video earlier. Temporal consistency is a big one. Making sure an object or person looks exactly the same from frame to frame, or that physics behave realistically over longer clips. Modders still struggle with that sometimes. You get weird artifacts or inconsistencies.
Yeah, I've seen some examples of that. What else?
Text rendering inside images. It's gotten way better, especially with models like SDXL and FLU XBot1, which specifically focused on it. But you still see misspelled words or text that looks kind of garbled or nonsensical sometimes. It's not fully solved. And a really fundamental challenge is memory requirements. VRAM. Generating high-resolution, high-quality images, especially with complex workflows involving ControlNet or multiple LoRa, still demands a lot of graphics card memory. Techniques like LoRa help because the adapters are small, and quantization can shrink models, but it's still a significant barrier for many people using consumer hardware.
Right, the VRAM issue is definitely a big one for accessibility. So, okay, challenges exist, but the innovation clearly isn't stopping. What's on the horizon? What emerging solutions or research trends are tackling these problems?
The pace is just relentless, really. We're seeing constant work on solutions. Things like more advanced quantization methods are being developed to shrink models even further without losing too much quality. New sampling algorithms and schedulers are appearing that promise faster generation speeds, getting closer to that real-time goal. Multimodal conditioning is a big area, using text, images, maybe even sketches together as input for more precise control.
And the link with language models, like you mentioned with DALL-E 3 and ChatGPT.
Exactly. That integration seems like a really powerful direction. Using sophisticated language models to help users refine prompts, brainstorm ideas, or even interact with the generation process more conversationally. We're also seeing research push towards unified architectures, models that aren't just for images or just for video or just for text, but single massive models that can potentially handle all of these modalities, maybe audio too. That could lead to incredibly comprehensive creative tools down the line.
A single AI for all kinds of creation.
Wow.
And what about the role of the open source community in pushing all this forward?
Oh, it's absolutely critical, cannot be overstated. While big labs like OpenAI and Google push the state of the art with models like Sora, so much of the innovation in accessibility, customization, tooling, things like LoRA becoming mainstream, interfaces like A1111 and Comfy UI, countless control net models that comes from the open source world. It's this incredibly vibrant ecosystem of researchers, developers, and artists sharing code, sharing models, building on each other's work. They foster collaboration, they rapidly test and refine new ideas, and they really democratize access to these powerful technologies. The field wouldn't be moving nearly this fast without them.
That's a great point. Okay, what an incredible journey we've been on today. We've unpacked the rise of diffusion models, how they conjure images from noise. We've seen how LoRA, ControlNet, and DreamBooth give us amazing power to personalize and control these creations. We looked at the evolution of the big models themselves, Stable Diffusion, DLE, the new FLUX.1 contender, and the diverse tools making it all usable, from Aeon and Comfy UI to diffusers, plus the exciting video frontiers with Sora, Runway, and Pika. So what does this all mean for you listening? Well, it seems the field is racing towards being even faster, easier to control, and more deeply integrated into all sorts of creative work. Powerful tools are becoming more reachable than ever.
Indeed. And if we connect this to the bigger picture, these systems aren't just technical novelties. They really do promise to fundamentally change how we think about, create, and even interact with visual media, professionally and personally. Which raises a really interesting question to maybe leave folks with. As these AI systems get better and better at simulating our physical world, understanding objects, physics, consistency, how might that change our own understanding, our own perception of what's real in this increasingly digital age?
That is definitely something to think about. A profound question indeed, as this tech continues its incredible trajectory. Thank you so much for breaking all that down for us today. And thank you all for joining us on this deep dive. We really hope you feel better equipped to navigate this fascinating, fast-changing landscape. Until next time, keep exploring, keep questioning, and keep learning.